Welcome, everyone. Today we are diving into an advanced MLOps topic, packaging a feature retrieval specification with your model artifact. Please note, while our provided training sources cover MFlow model registration, GitHub Actions, and deployment architecture, the specific mechanics of feature retrieval specifications and managed feature stores are drawn from external Azure Machine Learning documentation. You may want to independently verify that external information. Let's get started. Let's lay our foundation by discussing model registration. As outlined in our architecture sources, after your data science team successfully trains a Model A phase, we call the inner loop. It is essential to package and register that model in the Azure Machine Learning workspace. Why do we do this? Because without a central registry, deploying models consistently across different environments is nearly impossible. Typically, we package these models using MFlow. The deep dive here is that when you register a model as an MFlow model, you unlock a powerful capability called no-code deployment. This means Azure ML can automatically handle the scoring script and environment setup, saving your engineering team countless hours of manual configuration. Take a look at this flowchart. It illustrates the transition from the inner loop to the outer loop. We start with model training on the left. The output is packaged using MFlow and sent to the central model registry. Once safely registered and versioned, the model is perfectly positioned to leverage no-code deployment, streamlining our path to production. Now, we introduce a concept from outside our core sources to explain the why behind our main topic, the feature serving challenge. Imagine your model is deployed. During training, the model had access to massive tables of historical data. But in production, the consuming web application might only send a simple patient ID in its request. If your model requires 50 distinct medical features to make a prediction, it will fail. How do we bridge this gap? Historically, engineers had to write complex, custom data fetching logic directly inside the model's scoring script. This manual approach is highly prone to errors, creates latency, and is incredibly difficult to maintain as the data science team updates the model's required inputs. This diagram highlights the traditional, problematic workflow. The web app sends a simple patient ID. The scoring script receives it, but the model expects full feature data. Without a proper mechanism, this leads to a model failure, shown in red. If we use custom fetch logic to query a database, we often introduce high latency, creating a poor experience for the end user. To solve the serving challenge, we use a feature retrieval specification, another concept from external Azure ML best practices. What is it? It is a declarative configuration file that explicitly maps the model's required inputs to features living in an enterprise feature store. Instead of writing custom Python code to query databases, this specification simply tells the endpoint where the data lives. Why is this revolutionary? Because it completely removes data fetching logic from your scoring scripts. You simply place this YAML file alongside your model. During real-time inference, the underlying Azure infrastructure automatically reads the spec, looks up the necessary data using the provided primary keys, and feeds a perfectly formatted feature vector directly into the model. Let's walk through this sequence diagram of a modern inference request. The web app sends just the patient ID to the managed endpoint. The endpoint instantly reads the feature retrieval spec and automatically queries the feature store. The feature store returns the full medical history: age, blood pressure, BMI. The endpoint injects this complete vector into the ML model, which generates the prediction and returns it to the client. Fast, secure, and fully automated. How do we actually implement this? We package the feature retrieval specification directly into the MFlow model artifact. As we know from our sources, an MFlow model isn't just a single file. It's a directory containing model weights, environments, and configuration files. By saving the retrieval spec inside this exact directory, we guarantee that the model and its specific data dependencies are versioned together as a single, immutable unit. If the model requires a new feature next month, the versioned spec updates with it. The deep dive here connects back to our core capabilities, because this specification is neatly packaged inside the standard MFlow artifact. Azure Machine Learning can use its no-code deployment feature to automatically configure the endpoint's data connections without you writing any custom server code. This block diagram shows the anatomy of our packaged MFlow registered model. Inside the artifact, we have the model weights, the Conda environment, the standard ML model config, and our new addition, the feature retrieval specification. This entire package is passed as a single entity to the Azure ML no-code deployment engine, which reads all 4 components and spins up a fully functional live production endpoint. With our model correctly packaged, we must automate its deployment. Our training materials emphasize using GitHub Actions as the orchestration tool for our MLOps strategy. We define our deployment logic in YAML workflow files. Why? Because manual deployment is risky and slow. Automation allows for the rapid, reproducible delivery of machine learning artifacts. How do we do it? We store our Azure credentials securely in GitHub Secrets. The workflow uses these credentials to authenticate, then utilizes the Azure ML CLI v2 to register and deploy the model. For a deep dive, we trigger these workflows using feature-based development. When a developer merges a pull request, the push event automatically instructs Azure ML to register our mFlow model complete with its feature retrieval spec, ensuring total consistency. This flow visualizes our automated CI/CD pipeline. It starts when code is merged via a pull request. This acts as a trigger for our GitHub Actions YAML workflow. The workflow authenticates securely using stored Azure credentials. It then uses the Azure ML CLI v2 to register our packaged mFlow model, including the retrieval spec, and immediately deploys it to the managed endpoint. Deploying code automatically is powerful, but we must do it safely. As highlighted in our sources, to train, test, and deploy a machine learning model, it's best to use separate environments as part of your MLOps strategy. We use development, staging, and production environments. Why? Because if we update our feature retrieval specification and it maps to the wrong data column, we want it to fail in staging, not in the live application. How do we manage this? We configure environments directly in GitHub. The deep dive here is the implementation of approval gates. Before the GitHub action moves our packaged model from staging into production, the workflow pauses. A required human reviewer must verify the test results and explicitly approve the deployment, combining automation with strict quality control. Here we see the environment progression and the critical approval gate. The workflow automatically deploys our mFlow model to staging and runs integration tests. Then, it hits the GitHub approval gate. The pipeline stops. If a human reviewer analyzes the logs and rejects it, the pipeline halts. If they approve, the model safely transitions into the production environment. Let's apply all of this to a real-world scenario from our training text. Prosware is a healthcare startup building a web application to help practitioners diagnose diseases, specifically diabetes. The practitioner enters a patient's basic info, and the app requests a prediction from an online endpoint. However, to predict diabetes accurately, the model needs historical lab results and vital signs. We cannot expect the practitioner to manually type all that in. The solution, Prosware packages a feature retrieval spec with their mFlow model. When the app sends the patient ID, the endpoint instantly reads the spec, retrieves the patient's full medical history from the feature store, and runs the prediction. This provides the practitioner with life-saving insights in milliseconds, completely automatically. This flow visualizes the Prosware application. The doctor uses the UI to enter a patient ID. That makes an API call to our online endpoint. The endpoint, guided by the packaged feature retrieval spec, queries the medical feature store. The historical lab results are returned to the endpoint, scored by the diabetes model, and the prediction is sent right back to the doctor's screen. We conclude by looking at the big picture, completing the outer loop. As our architecture sources show, MLOps is divided into the inner loop of development and the outer loop of deployment and monitoring. Our goal is to seamlessly transition models between these phases. Why is this critical? Because models degrade over time due to data drift, and they must be retrained and redeployed continuously. By combining Flow's standardized packaging with GitHub Actions, we achieve this. The deepest insight here is version safety, because the feature retrieval specification is packaged directly inside the mFlow model artifact. They are inextricably linked. If your team retrains the model to require a new health feature, the updated spec is deployed simultaneously. There is zero risk of version mismatch between the model code and the data fetching infrastructure. Our final sequence diagram shows the continuous MLOps cycle. The inner loop pushes model v2 along with its updated feature retrieval spec to GitHub. The CI/CD pipeline runs automated tests in staging. It then deploys the mFlow artifact to the outer loop. The production endpoint automatically configures the new feature lookups based on the spec. Finally, monitoring telemetry feeds back to the data science team, restarting the cycle.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. We have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.